So till now, I have just covered about the very basic of lumped capacitance model and the technical requirement of Biot number to be less than 0.1, and solved some 3 questions in the previous class where we concluded that a concrete and a wall structure can possibly be modeled as my lumped capacitance, and hence we can go ahead and develop some equations which we already have from my lumped capacitance module of heat transfer. So I'm just going to summarize that thing which is helpful over here in this module currently. So we are concerned about the equations. For lumped capacitance. So there are 3 major equations which we are concerned about. The first is the differential equation. The second, so now this is not an original Navier-Stokes equation. This is the differential equation which is connected with the lumped capacitance. This is the simplified differential equation. We'll not solve the simplified differential equation also in whole step-by-step manner. I'll just directly give you the solution for temperature T, which is changing with time. So that is one of the only factor which is available in lumped capacitance. Otherwise the temperature can change with space and that is location and time. But with the lumped capacitance model, we are dropping all the spatial coordinates and assuming that everywhere inside my body, my temperature is constant. So the temperature can change with time, but it cannot change with location. So location is not a variable now. And the third, heat transfer, which is happening in time T. So as the temperature changes, because of some temperature differences, there are some temperature changes in our body also, in the body of our concern, and because of the temperature changes, there are heat transfer happening, or the correct manner could be because of the temperature gradient between, not inside the body, between the body and the outside, the surrounding, there will be some heat transfer from the surface, and because of that heat transfer, the temperature of the body will change, and that change of temperature is defined by T, changing with respect to some time T, and the total heat transfer which occurs from the body to surrounding or from surrounding to body is defined by Q. So these are the 3 things we are concerned about. And let's start with the differential equation. So the differential equation is given by Q U into A, which is total temperature of my mass at some time T minus temperature of outside, which is equal to, so this is the temperature of the mass, and hence this is also given as rho V C dt by dt. So change of temperature with respect to the time of the mass is equal to the heat transfer which is happening from the mass. So if we have a mass or any body, the change of temperature, the change of energy of the body is given by this factor, and the same change of energy is happening because of the heat transfer from the surface, and the amount of heat transfer is given by this. So the amount of heat transfer should be equal to the amount of energy change in the body. Now, right, after we solve this differential equation, obviously this much differential equation with respect to time, so we integrate this and we get the solution for temperature. The solution for temperature is given by Tm at some time T minus T out upon Tm at T is equal to 0. That's the initial temperature of my mass, minus T out is given by exponential of minus UA into total time T. this is the time factor T, which is I am representing by small t, and the capital T means temperature, divided by rho V C. Since it is a solid, Cp or Cv doesn't come. For gases, the Cp comes, but for solids, the Cp is equal to Cp, Cv is equal to a specific heat capacity of my solid. So this is one of the temperature, which is I'm giving the solution for the temperature, and the total amount of heat transfer is given by Q. I hope it is not cut down. Yeah. And the Q total is given by rho Vc into Tm. T is equal to 0. Initial temperature of my body minus T out into 1 minus exponential of minus UAT upon rho Vc. I hope the formula is very much clear to you and it is completely visible to you. Now let me just give you all the factors which I have used, so it's easy for you to understand and relate between the things. There's no confusion left out. So these are the 3 formulas which are important. Let me just define this. So my UA is from UA delta T. Using the Newton's law of concept, this U is the overall heat transfer coefficient into A is overall heat transfer coefficient, right? A, area of heat transfer. My Tm is temperature of mass, and so Tm is a function of time, right? And my Tmo or Tm0 is the initial temperature of my body. Then the small t is the time, the duration. The rho is the density of my material. V is the total volume of body. C is the specific heat capacity. Right? So I think everything is clear to you. I have defined all the factors, and in total, these are the 2 equations which we are going to use extensively in this module to solve for temperature. If there is an outside temperature T out, so this is outside temperature also, which I skipped or missed out. Outside or ambient temperature. And one of the very assumption of my model is that the outside temperature is constant. The outside temperature doesn't change with time. So what we have, if I have some given outside temperature and the initial temperature of mass, let's say the outside temperature is 30 degrees Celsius, my initial temperature is 75 degrees Celsius, and UA value of my building envelope is available, rho Vcp of my building is known. So we can calculate the temperature of my building, temperature of concrete or temperature of the wall or temperature of air inside my building after, let's say, sometime 6 hours, 10 hours, 20 hours, and this formula will be helpful. And in the similar way, if we want to calculate the amount of heat lost from the building, because outside temperature is lower, inside temperature was higher earlier. So with time we are going to lose heat to the ambient, and this formula will help us to calculate the amount of heat transfer from my building to ambient in some time t. So I hope you have understood. Thank you.